I wanted next to jump into like what are the good and bad of structural equation models.
Yeah, so like you said, they're essentially like more complex versions or more general versions of regression models or path models where you have latent variables and multiple indicators. And so with this complexity comes the tendency to misspecify models because there are many ways in which structural equation models can be wrong. And one of the strengths of them is that they can be tested against the data. So most structural equation models will be over-identified, which means that they place testable restrictions on the covariance and or mean structure of the variables, for example, by setting certain paths implicitly or explicitly to 0. So you can test them with model fit tests, but then as the model grows larger, there are many ways in which a model could be wrong. And often they are wrong, and people accept them nonetheless. And they'll say, oh, they're an approximately okay fit. And so that can come with bias. So if you accept an incorrect model that doesn't really fit your data, then it's like wishful thinking a little bit. So the effects that are in the model may be incorrect, may be biased. And you have the same problems as in regression and path analysis and mediation analysis when you have omitted variables. Also, then it can be biased. So it's not per se a causal model, but it makes causal assumptions, and those may be right or wrong. People often apply structural equation models, at least in my field in psychology, to cross-sectional data, which doesn't allow you to say anything about causality really. So if you have measured all the variables at the same time point, and there's no experimental manipulation of anything, you don't fulfill the criteria of temporal precedence or necessarily control of all potential confounding variables. So you have issues there. And so that this is what I often see is that people try to overcome flawed design or flawed measurement by fitting ever more complex structural equation models. And they think with fancy statistics, they can mitigate the design problems. And that's really not the case. So structural equation models work great when you also have a great design and you have great measurement. And it can help you overcome some of the measurement error problems if you have random measurement error. However, it can't overcome fundamentally flawed research designs. And so people oftentimes draw conclusions from these models that are not warranted. So there are many also instances where an equivalent model is present. So you could have the same implied data structure, so a model that fits equally well, but that makes different causal assumptions, and it would fit equally well or better. So you can never prove with a structural equation model that your causal assumptions are correct. You can only falsify models that are incorrect. So if the model fit test says that the model doesn't fit, then that rejects your hypotheses. Or if you find that the paths that you hypothesized are 0 or near 0, then that can falsify your assumptions, but you could never prove that something is causal. And that's something that many people misunderstand. So they fit a structural equation model, and then they think if it fits well, and if the paths are significant, then that proves the causal assumptions. And that's really a mistake to think that, in particular when you have cross-sectional non-experimental data.